Hello everyone, welcome to Introduction to Seismic Isolation webinar. I am Gianni Kubin from ProtaSoftware's Business Development Team. Today we are hosting Mr. Bahadır Şadan, General Manager of OBS Earthquake Engineering, one of the prestigious engineering firms of Turkey. He is also Assistant Professor at MEF University. So our agenda for today, I will quickly go over Prota and ProtaSoftware technology solutions. After that, I will pass over to Dr. Şadan for his presentation, where he will present important topics such as seismic isolation and seismic isolated building design. So Prota Group was founded in 1985 and is now a leading global software development, engineering, and consultancy group. The Prota Group comprises of 6 companies. I'm here representing ProtaSoftware, the founder of ProtaStructure suite. Prota Polska and Prota Asia are international branches of ProtaSoftware. So as you can see on this map, we are an expanding company and growing every year. Today we operate with more than 15 offices located in Malaysia, Singapore, Philippines, Poland, and Turkey. We are planning to open up another office in Berlin, Germany in near future to increase our services in Western Europe. So besides our regional offices, we support our users and provide services through our channel partners all around the world. Here, I want to briefly summarize some of the milestones of ProtaSoftware's journey throughout the years. In 1992, Prota launched Probina Orion, which is the world's first concrete building design and detailing system. In 2005, Probina Orion provides first building solution for retrofit and rehabilitation. In 2007, Prota invested in BIM technology and launched ProtaBIM, which provides bidirectional physical model integration with leading BIM platforms. In 2014, ProtaSoftware introduced the revolutionary ProtaStructure suite. In 2015, Prota delivered an entire metro line with BIM technology. And in 2018, Prota's engineering team delivered the world's largest passenger terminal building in Istanbul. So the structural design of this entire terminal building was delivered with ProtaStructure. So ProtaSoftware's latest technology solutions available for the structural engineering market, we have ProtaStructure for modeling, analysis and design of your structures. Prota Details for your automated detail drawings. It includes intelligent rebars and design libraries such as retaining wall, scaffold design and detailing. Prota Steel is our latest technology solution of your steel detailing and connection design of your structures. There is drawings and calculation reports within this technology. And we have Prota BIM, which is our BIM tool to bidirectionally link your models with other BIM platforms like Autodesk, Revit. So modeling, analysis, design, detailing, fabrication, and BIM. We are very proud to introduce our latest structural BIM design software solution, ProtaStructure 2021. So the Prota advantage is that it is a complete package for modeling, analysis, design, detailing, fabrication, and BIM. Now I would like to hand over to Dr. Şadan for his introduction to seismic design presentation. Dr. Şadan has a PhD degree in structural engineering from Politecnico di Milano. Having nearly 20 years of global structural engineering experience, by the way, he used to work at a managerial level at Prota Engineering, he founded his own company, OBS Earthquake Engineering. Dr. Şadan is an expert in earthquake engineering, earthquake resistant structures, seismic assessment, and retrofit of existing buildings. He has also played an active role in the preparation of special rules for design of seismic isolated building section in the new Turkish seismic code for buildings. Thank you. Ms. Dr. Şadan, you can start your presentation.
Hello, everyone. Yes. Hello, everyone. Thank you very much, Mr. Gianni Kubin. Thank you very much for Prota for giving me this opportunity to share you my experience on seismic isolation. Today, I will make you a presentation about the introduction to seismic isolation. I will introduce you the basics and the principles of seismic isolation, and at the end, I will introduce you to seismic isolation applications that we completed while I was working at Prota in between 2010 and 2013. Let me share my screen now. Okay. So Mr. Kubin just introduced me, but just to summarize again, I have a civil engineering BSc degree from Istanbul Yıldız Technical University. Then had my master's degree on earthquake engineering at Boğaziçi University, Kandilli Observatory and Earthquake Research Institute. Then had my PhD degree in Politecnico di Milano in Italy. Then when I returned back from Italy, I worked at Prota Engineering for three years as an earthquake engineering division manager. Now in 2013 I founded OBS Earthquake Engineering Solutions, and for the last 3 years I am also an assistant professor at MEF University in Istanbul. Besides professional activities, I am also I'm executive board member in some associations like Turkish Association for Seismic Isolation and an international association, which is Anti-Seismic Systems International Society. In today's presentation, first I will talk about the strength-based design, give a little bit information about performance-based design, where we actually nearly 3 weeks ago or a month ago, Dr. Tüzün introduced performance-based design. Then I will talk about principles of seismic isolation, the history of seismic isolation, the isolator types, seismic codes, isolator tests, and give you some photos and information about seismic isolation applications worldwide. Let's start with strength-based design. Why I start with strength-based design is that unless you are performing a nonlinear analysis, the design that you are following the seismic codes worldwide is a strength-based design. When we say strength-based design, it means that you calculate an equivalent seismic force acting on the building, you distribute this seismic force, and you provide sufficient strength for your building to resist these seismic forces. Like in this example, we can see a bridge band here with the mass concentrated on the deck level. When there is an earthquake excitation, the seismic forces, inertial seismic forces, are acting on the mass of the structure. Then, as a response, some moments, base shears are developed in the structural system, and you design your system. If we designed this bridge band as elastic, then the structural elements should have had sufficient capacity to resist these seismic forces without any damages. However, what we do in strength-based design is not like that. What we do is we divide the elastic forces by a strength reduction factor. Sometimes it is called behavior factor, and we design our structures to this level of seismic force. This means that, however, the seismic forces are acting at this level, and we design our structure at this level of seismic forces. This means that some damage will occur in our structural elements, but our structural system should have enough capacity to resist this deformations. this was the design for seismic forces. However, design for normal loads, what we call dead load, live load, wind load, snow load, traffic load, is different than design for seismic loads. In design for normal loads, we do not want any damage from our structure. We provide sufficient strength to our structural members to resist the normal loads without any damage. However, for seismic actions, it is opposite. We provide less strength than the seismic forces, and we accept that our building will go beyond the elastic deformation and it will suffer some deformation and damages, but the building needs to be stable at the end of the earthquake without a total collapse. This is how we design for normal loads. As you see, these are the levels. This is the level for dead load plus live load. Then we increase it with some factors. Plus, we have some margins for the material strength, where we reduce the strength of characteristic strength of materials by some factors. They are different in different codes. Actually, where we have to design our structure is at this level, dead plus live load. However, we have a margin of safety here, a great margin of safety to resist the normal loads. In seismic design, it is a little bit different. This is actually the demand of earthquake, the force level that the earthquake that develops when an earthquake hits the structure. But we design our structure at this level, dead load plus earthquake load divided by a force reduction factor. We design our structure at this level. However, we might have a little bit higher strength due to the reduced material strength. The expected strength of the material might be a little bit larger at this level. And after this level, the building goes, the building gets damaged, and some hinge mechanism starts to develop. The building should have enough capacity to resist this level of deformation. The deformation level depends on the seismic, the amount of seismic action. I mean, for a service level earthquake, which we can say an earthquake with a return period of about 50 years, the deformation will be very limited. Maybe some minor cracks, some hairline cracks that can be repairable. For the design level earthquake, where you design your structure, the building will go a big amount of non-linear deformation, which means damage in the building, that can be repaired or maybe not repaired after an earthquake. And for the extreme level earthquake, where we design special structures like hospitals or highway structures, important structures, the building goes further deformation and it should not collapse at the extreme level earthquake. So when we say earthquake resistant design, I put an exclamation mark here, because when we say earthquake resistant, the people might think that the building will not suffer any damage. But when we say earthquake resistant design, the civil engineers, when say earthquake resistant design, this means that there will be damage in the building after a major earthquake. The earthquake resistant design relies on the damage under the design earthquake. Let's see a building that was a full-scale building that was tested in Japan and at E-Defense Laboratory, and let's see how it behaves. It's a conventional design. When you see there are deformations, I mean, because of the relative drifts of the stories, there are deformations, especially in the beam column joints, and this is expected. When we do a strength-based design, we have to follow the capacity design rules to to have the damage at the desired locations of our building and not to have collapse. However, let's pass this part. And this is a figure showing the damage levels in increasing magnitudes of earthquakes. After a part, there will be a life safety where we generally design our structures for life safety performance level. And beyond that, there is the collapse prevention level for a higher earthquake hazard level. Even though, if you say that for an important structure, for example, let's talk about a hospital, you can say that, okay, this is a hospital, it's an important structure, so I have an importance factor of, or in Turkish code, this is 1.5. This means that you are increasing the design force, that you are increasing the seismic force that you are designing your structure by 1.5, by multiplying it by 1.5. Yes, you can have a structure, a building that can resist the seismic actions. Maybe there won't be any structural damage, or maybe there might be some minor cracks that can be repairable after an earthquake. However, when you go inside, you might experience a scene like this. I mean, these are buildings. For example, the one on the top, it was a building that we visited while we went to the Seismic Isolation Conference in New Zealand in 2017. There was an earthquake. The building was designed with modern codes in strength-based design. This is the view from outside. I mean, this photo was taken by us from outside after an earthquake that happened something like 150 kilometers away from the epicenter. And this is the visual, the photo, the scene from the inside. I mean, even though you can protect the structural system from the earthquakes, inside you might experience a scene like this. Or these are some scenes from other earthquakes, an airport and a hospital. I mean, a hospital that you designed by an importance factor of 1.5 may seem undamaged from outside, but inside you might see a scene like this, and you cannot use the hospital after an earthquake that you really need after an earthquake. So this was the problem. I mean, you can protect maybe the structure, you can have some minor damages in your structure, but it is very, very hard to protect the non-structural components in a building. Whether you have to make a special seismic design of non-structural members, which can go very expensive, or you can isolate the building. This is the solution of the problem. So let's talk about, let's talk about the seismic isolation. I mean, at this seminar, we will not talk about the seismic design of non-structural members, but we will talk about seismic isolation of buildings. What is seismic isolation? In a conventional design, during an earthquake, the building moves like this. I mean, there are deformation at story levels, and due to the relative drift of the story levels, and these deformations in the column beam joints create damage, and the building might not be used after after the design level earthquake, might not need to be retrofitted, or maybe demolished and reconstructed. The earthquake has a demand, has a displacement demand on the building, and the displacement demand for such a building, for a conventional design building, is provided by the relative story drifts. However, in a seismic isolated structure, you decouple the building from the ground level. You put some members, some bearings that are very flexible in the lateral direction, but very stiff in the vertical direction, so that they can carry the vertical load of the building, but during an earthquake they can move in a lateral direction. The demand of the displacement demand of the earthquake is provided by the seismic isolators in this case. How it works? How seismic isolation works is that the vibration properties of the building is modified by installing the isolators. As such, the destructive signals of the seismic event is reduced. I mean, there are two figures here. One is seismic isolator on the left. The other one is the conventionally designed building. You can see that during a seismic event, the inhabitants of the building might not even notice that there was an earthquake, and all the structural and non-structural members are protected in a seismic building. However, in conventional design, you can see that even though maybe the building does not collapse, you can see that non-structural components fall down, some mechanical equipments, the pipes can break, and the building might not be used after an earthquake. So the main benefit of seismic isolation can be the reduction of the story drifts, which is related to the damage in the building, reduction of story accelerations, which means that you reduce the seismic force acting on the building. Hence reduction of structural member forces. Let's see a similar test for a seismic isolated building that was tested in Japan, a shake table test. Below you see a blue surface, that is the shake table itself, and the green pistons on the left, that gives that simulates the earthquake for this building. The building is a reinforced concrete building that was designed as a hospital. You can see the furnitures in the building, and below there are seismic isolators, and it's a strong shake. Actually, the building moves over the shake table, which represents the ground. It floats nearly. What you see is that only the sliding components of the building and the roller furnitures move in the building, but the overall system does not get damaged, and there are no non-structural damages in the building. If this was a conventional design building, you will see both structural damage and non-structural damage at the same time. This is another video recording that was recorded during Tohoku earthquake. Maybe it is a little bit further than the epicenter of the earthquake, but here you see the ground level column. The seismic action started, the earthquake started. You see that only the actually ground moves, but the building is like floating on the isolator, which is black member here. And here you see the displacement that it makes. Since it is a little bit far away from the epicenter, the displacement levels are nearly 10 centimeters. And here you can see the acceleration records in the ground floor and above the isolator. And you can see that it is the acceleration levels are reduced nearly maybe 3 times, 4 times. Another footage from an earthquake in Japan, again, I guess. This is the building, seismic isolated building. Please notice the shoes on the ground and the building here. And when the seismic action starts, actually the ground moves, not the building again. And you can see how the building reacts to the earthquake. You see how the ground displaces during the seismic event, but the building stands still. Yes, we talked about how good seismic isolation is. It's a new technology. No, actually, it is not a new technology. In the history, it has been used, maybe consciously or unconsciously, several times. For example, one example is a tomb in Iran, today's Iran. It's the tomb of Kirosh in a Persian emperor. When they designed this tomb, they over the ground they put the stones act like foundation without any connections to the ground and without any connection between each other. So during an earthquake, these stones move on top of each other, and by friction they damp the earthquake forces, and this tomb is still standing still after several hundreds of years. Another example might be the Greek temples. No, you can see Greek temples standing like that. They are very vulnerable structures. They are constructed on stiff soil with a sand level on top. So during an earthquake, the temple moves on the sand layer, and they do not get harmed, or at least they get less damage than a conventional design. Another example from Istanbul, an obelisk, Theodosius stone, that was constructed, that was placed in Istanbul Sultanahmet Square after Christ at 4th century. It is nearly 20 meters high, but it's still there. After several earthquakes, it still stands there, just by the help of 4 little bronze cubes below the stone that moves during an earthquake, that rocks, which is a similar seismic isolation principle during an earthquake, and it's still there. It's a very vulnerable structure, but it's still there, slender structure, but it's still there. And beginning from the 19th century, the people tried to make this a market product. First known patent application was in 1870. A patent application for a building resting on 2 concave plates with some rollers inside. Then in 1897, again, 2 concave surfaces under a building with a single articulated block, which is very similar to the modern friction pendulum devices. In 1906, again, a patent application we see. Then a medical doctor in England thought that if we could put some slippery mineral below the building, a salt powder, it may help the building to slide on this slippery mineral. But until 1974, there was not a market product. In 1974, William Robinson, who invented the lead rubber bearings in New Zealand, and we are still using these lead rubber bearings in our buildings. I will talk more about lead rubber bearings, but lead rubber bearings are composed of rubber layers to give the lateral flexibility to the bearing, the steel shims to give the vertical stiffness to the rubber isolator, and the lead core inside just to provide additional damping to the bearing. Then in 1985, Victor Zayas in USA invented the first prototype of friction pendulum bearings, sliding bearing, friction pendulum, or curved surface sliders, let's say. There is a concave surface and a sliding puck inside, which during an earthquake moves, and by the help of friction, it dissipates energy. And the first applications of seismic isolation with real seismic isolators, but they were all rubber isolators actually, not lead rubber isolators, but rubber isolators. We first see in Japan, in Tokyo in 1921, Imperial Hotel. It survived the big Kanto earthquake in 1923. This was the information that we could find in the literature. It survived with minimum damage actually, while the other buildings around were getting high damages. The another building in Europe, in former Yugoslavian Republic of Macedonia, the Pestalozzi school in 1969 was constructed over the rubber isolators. Then actually they put rubber blocks there as isolators, but they did not put steel shims where I showed here. I mean, there are steel shims. So they did not put steel shims. So you can see that by the axial load acting on them, in time, they started to make bulges around. So in time, maybe 20 years after the construction, they removed those isolators and installed the lead rubber isolators instead. They tested also these isolators and compared the initial testing results with the test results, let's say 20 years later, and the results were very similar. So yes, there are some effects of aging, but not that much. So how do these isolators work and how do they protect our buildings from severe seismic actions? Actually, there are two effects of seismic isolation. The primary effect of seismic isolation is the period elongation. You know, when you construct a traditional building, reinforced concrete building, let's say, the building natural vibration period depends between, let's say, 0.3 to 1 second. Let's make a guess. If the building is 5-story, for example, or 6-story, then we can say that the natural period of vibration is 0.6 seconds. And when you check, this could be a acceleration response spectrum, or this can be a base shear period graphic. You can see that in the lower ranges of the period, there are higher accelerations acting on the building and higher forces. So when you design a conventional building, the seismic forces acting are high. But in seismic isolation, the building periods are around between 2.5 and 5 seconds due to the lateral flexibility of the isolators. So you shift the period from 0.5 seconds, let's say, to maybe 4 seconds. And there is a great reduction in the acceleration response spectrum with the elongation of the period. So less seismic forces are acting on the building. But however, when you increase the period, you also increase the demand of the displacement demand of the earthquake. As I said, for a conventional design, the displacement demand of the earthquake is provided by the relative drift of the stories in a building. However, in seismic isolation, this displacement demand of the earthquake is provided by the displacement of the isolator. So when you increase the isolation period, you will increase the displacement demand on the isolator. So you have to have isolators with larger displacement capacity. This was the first effect, the period elongation. The secondary effect is increasing the damping of the structure. In a conventionally constructed building, let's say reinforced concrete structure, the modern codes say that you can deploy 5% damping for the design of your structure. This is related to the friction between the concrete material, some damages, some crack openings and closings, those kind of things. This is related to the damage actually, the 5% damping. In seismic isolated structures, this damping is between 10% and 40%, in average 20-25%. And what does this damping does? What does this damping do to our structure? This, with the increasing damping, the displacement demand is decreased. So if you increase the damping, there will be less story displacements and less demand from the isolator displacements. And when you decrease the demand, also you decrease the force as well. So you, with increasing demand, you decrease the displacements and also the accelerations acting on the building. Let's talk about the isolator types. The topic is very large topic. I mean, there are several things to talk about, but I'm just giving you the basic things that you might need to know. I'm introducing you to the seismic isolation. So if you want to go further, please check some literature, or maybe we can make another seminar on more details in seismic isolated building design. So what are the isolator types? There are two main isolator types that are being used in the world. One of them is rubber bearings, the other one is friction, curved surface friction isolators. So let's talk about first rubber bearings. As the name goes, the main compound is the rubber, and rubber is extracted from the rubber trees like this, and every day they make a scratch on these trees and they collect the rubber compound. Then with applying some additional materials and with heat, they vulcanize this rubber and they create the rubber that we are using for seismic isolators, and also for the other rubber compounds that you see in the daily life. For example, the tires of the cars or the soles of your shoes. All of them are composed from this rubber material. And the top 5 rubber producing countries are given here. Maybe it's one of yours countries. Thailand, the main producer, Indonesia, Malaysia, India, Vietnam. So it depends on this the product of these countries mostly. So if you want to produce your own rubber isolator, you have to import the rubber compound in one of the countries that has the rubber trees. What are the rubber bearing types? Actually, there are 3 rubber bearing types: low damping rubber bearings, high damping rubber bearings, and lead rubber bearings. Low damping rubber bearings and high damping rubber bearings, when you make a section cut, they look like this. I mean, there are rubber layers and there are steel shims that make the vertical stiffness, that provides the vertical stiffness. In high damping rubbers, different than the low damping rubbers, there are some additional materials added to the rubber compound, which are called carbon black, and it gives by adding these compounds, the damping capacity of the bearing increases. The low damping rubber bearings are not commonly used alone. They are used with additional dampers mostly, because I said, if you remember that I said there are 2 effects of isolators. One is the primary effect was period elongation. Yes, you can achieve with low damping rubbers. The other one was additional damping, which you cannot achieve with low damping rubbers. So you need high damping rubber bearings, or you need additional dampers that are used with low damping rubber bearings together. Other than this, there are lead rubber bearings, as I said, that you make a hole inside the same low damping rubber bearing compound and you plug the lead inside. So the damping is provided by the lead inside. You might ask, okay, this isolator displaces like maybe 50 centimeters in 360 degrees in both directions. How it returns back? This is rubber. Rubber is elastic. When you pull the rubber, it displaces, it elongates. When you leave it, it comes back to the original position. So it's the same. When it displaces, the building displaces, then the rubber itself is pulling back the building to the original position, recenters. Let's see a rubber bearing in action. A test, seismic isolator test. You see that rubber bearing displaces. This is a real ground motion record applied to the isolator. But normally we do not do this in the test according to the course. We mostly apply the seismic action in single direction, unidirection, sometimes bidirectionally, but mostly unidirectionally. Let's see a test from the same testing facility, a shake table test. And you can see the rubber isolator here on the left. with some cross-linear bearings adapted. You see that the bearing moves, the building moves on the bearing. There is a lot of displacement. You can see that maybe 60 centimeters, 70 centimeters displacement. Only the furnitures with rollers or suspended things move in the building, but you do not experience any damage to the structural and non-structural components. If it was a conventional design building, you would see a lot damage. How do we model rubber bearings? This is very simply showing you an illustration of bilinear representation of rubber bearings, actually mostly lead rubber bearings. How do they behave? There is a first initial branch here, initial stiffness, elastic stiffness branch, which depends on actually, I mean, this initial branch you only see in the first loading phase. After that, the isolator moves in this curve, in the secondary slope, secondary stiffness branch. This is a force displacement representation. When we design the rubber bearings in the softwares that we use, it can be any software, we mostly use this bilinear representation with the initial stiffness, then the secondary stiffness. If we know all the components of this bilinear representation, then we can model the lead rubber bearings easily. The first initial branch is the K1, the initial stiffness, which depends on the secondary stiffness actually, and also which depends on the lead plug inside, the properties of lead plug inside. The secondary stiffness depends on the rubber compound only. I mean, if you change the size of your isolator or the shear modulus of the rubber compound, then you can change the secondary stiffness. You need, I mean, you can calculate the initial stiffness by multiplying actually approximately, this can be 9 or 10 or maybe 11, maybe sometimes 8, but mostly 10 times the secondary stiffness, and you can model it like this. If you know the yield force and the yield displacement, then you can easily model this. Yield force, I mean, to calculate the yield force, you need the characteristic strength, which is the force that intersects the y-axis here, this point. And it depends totally on the lead plug properties. You can, if you know the area of the lead plug, and if you multiply it by the shear strength of the lead plug, then you can calculate the characteristic strength. Then from the similarity equations, you can easily find the F by yield force, and then if you know the yield force and if you know the initial stiffness, you can calculate the yield displacement, and you can have this bilinear representation. And if you adopt this in any software, you can do your analysis with seismic isolators. When we design, we first do an equivalent linear analysis, and first we do equivalent linear analysis, then we do non-linear time history analysis, because the rubber behavior is highly non-linear, so we need non-linear time history analysis. But every time we compare the results of non-linear time history analysis with equivalent linear analysis. And when you do equivalent linear analysis, you have to know how much equivalent damping is obtained by the isolation system. So you need to calculate this. And the damping in this case is the energy depending on the energy dissipated in a cycle. If you calculate the area of this cycle, if you take it like a trapezoid and calculate the area inside, which is WD here, energy dissipated per cycle, and if you use this formulation, which comes from a sinusoidal waveform, if you calculate this equation, then you can calculate the equivalent damping to your structure. So if it is 20%, here is a table from American code, ASCE. If it is 20%, it says that you can reduce the 5% acceleration spectrum by 1.5. If it is, for example, let's check the 5%, what you use generally in your design, then the factor is 1. If it is 20%, 1.5. If it is more than 50%, then you can reduce the acceleration spectrum by 2, factor of 2. The other type that we commonly use is the curved surface sliders. I prefer to say curved surface sliders because friction pendulum is a product specific term. I mean, the first, I told you Victor Zayas, he first called friction pendulum, so it's a product specific term. So in general terms, we can say curved surface sliders. How they behave is actually very simple. It's a pendulum motion. You have a curved surface, use like here. Now we will see the curved surface plate. On top, a slider, then an upper plate, and you construct your building on top of this. So the pendulum motion is independent of the building itself. No, if you know the length of your the radius of the pendulum, the radius of curvature of your isolator, then you can easily calculate the period of vibration of your structure. It is period equals to 2 pi square root of the radius of curvature divided by the acceleration of gravity. You can take a rope with a mass down, you can make it vibrate. The vibration period will not change with the force acting on it. It will always be the same. So this depends on this. It's very easy to calculate the equivalent linear properties of friction isolators, and it depends on the pendulum motion. There are 3 types of pendulum isolators commonly used. The first invented one was single concave pendulum isolators, but this had some problems. The main problem is it depends on the friction. So when there is friction, there is heat, and when there is heat, the friction coefficient drops down. So if it is a high seismic region during an earthquake, this will move. The upper concave plate will move on the lower concave plate. Upper plate will move on the lower concave plate, and there will be a lot heat develops here. So there will be a reduction in the friction coefficient, and also the displacement capacity is limited. I mean, if you want to have a 50 centimeter displacement capacity isolator, then at least this lower plate should have a diameter of 1 meter. No? 50 centimeters here, 50 centimeters here. Then double concave pendulum isolators were invented by the same inventor, Victor Zayas, actually. How it works? Now you have double concave plates. So the displacement is, the size is actually halved. The first motion, let's say, starts in the lower part, 25 centimeters, then with the upper part 25 centimeters. So when you have 1 meter diameter isolator here, you can have 50 centimeter diameter isolator here. Plus since there are 2 sliding surfaces, also the heat effects are reduced. Heat effects are halved as well. So it's a now mostly we use double concave pendulums in our designs. Now there is the third invention by Victor Zayas. After the patent expires for the double concave and single pendulum, he invented triple friction pendulum isolators. Actually, this doesn't mean that there are 3 different surfaces. Actually, there are 4 surfaces. You can see that there is an initial part here. There are 2 surfaces here and 2 surfaces here, but there are 3 friction. He can adopt 3 friction coefficients for 3 different surfaces. 1 friction coefficient here, 1 friction coefficient here, and 1 friction coefficient in this part. And there is a lower friction in this interior part, like let's say less than 1%. So during a small earthquake, even with a small earthquake, this isolator starts to move. In other type of isolators, let's say that the dynamic friction is 5%, unless the 5% of the seismic weight of the building acts on the structure, they do not move. They act like a conventional building. It means that after some level of earthquake, they start to move. Before that, they move like a conventional building design. This has a great advantage on that. With even a small earthquake, they start to move. So it gives you comfort during an earthquake. I mean, with a 4 magnitude earthquake, 5 magnitude earthquake, you do not want to feel the fear of earthquake like the other conventional building design. So this has a great advantage on that. Let's see the difference between triple pendulum bearing and a single pendulum bearing from this illustration. You see that a single pendulum bearing moves on a single surface, but a triple friction pendulum, first the motion starts in the interior part with less friction. Let's see it again. With less friction, less than 1%, let's say, then moves on the upper and lower place. The difference is this. Let's see a triple friction pendulum in action. Again, in the same laboratory, a shake table test. Again, a hospital. It is adapted as a hospital. You can see the displacement, maybe again 60-70 centimeters, and the building stands still. How do we model friction pendulum isolators? A binary representation. Actually, it is easier than rubber bearings. Everything depends on the friction actually and the radius of curvature. Okay, so the initial stiffness is nearly infinite. It's very high. When it starts to move, I mean, you increase the force. Let's say this is my mobile phone. I increase the force, it doesn't move. It's in this level. I increase the force more and more and more, and after a time, it starts to move. And it is this point. So it is the point that the friction force is beaten. This is this point. You know the friction coefficient, and the friction depends on the axial load on it. If you know the axial load, you can calculate this point. Then the secondary stiffness is totally depending on the radius of curvature, because when you push something, when you push a structure, let's say, after it starts to move, after you beat the friction, the friction, I mean, the force stays constant. It doesn't change. Here, the only change in the force because of this secondary stiffness is due to the curvature itself. I mean, the radius of curvature. So if you make a smaller radius of curvature, which makes a smaller sphere, a part of a smaller sphere, then this stiffness is higher. If you make it more flat, if it is totally flat, this would be a rectangle. I mean, it will be flat here also. But since there is a curvature, then it behaves like that. And the secondary stiffness is depending on the axial load on it and the radius of curvature. So if you want to calculate the maximum force, then you can sum up the force here, that first it starts to move, and the force that you calculate by the secondary stiffness. If you multiply it with the displacement, any displacement you want, then you can calculate it, and you can calculate it easily. And if you want to know the effective stiffness, you can make the second stiffness to this level. So if you know the mass of your structure, and if you know the effective stiffness, then you can calculate the effective period of your structure. And if you are doing an equivalent analysis, you will need the damping, equivalent damping. It's again the same. If you calculate the area inside and put it into the formulation, then you calculate the equivalent damping, and again the same. If you have 20% damping, equivalent damping, then you can reduce the acceleration response spectrum by 1.5. what are the codes that are followed? I might miss some of the codes. Sorry if there are other codes that are not mentioned in the seminar. If you are using another code, please write in the comment part so that I know. The American codes are mostly commonly used in the world, mostly ASCE 716, chapter 17 of ASCE 716. Then if it is a bridge with isolators, then you use the ASHTO, guide specifications for seismic isolation design. There are European codes, Eurocode 8. There is a chapter for seismic isolated building design in Eurocode 8, EN 1998-1. For the bridges, seismic isolated bridges, you have to apply to EN 1998-2. And for the isolation devices, isolators, anti-seismic devices itself, you have to use EN 15129 code. There are really detailed information about the design of isolators, the isolator components, the tests in this code. It was published in 2009. I think still the official version of the new revised version has not yet been officially published. I'm not so sure, but there should be a revision very soon on that. As far as I collected information, there is a seismic isolated building design code in China, in Mexico, in Taiwan, in Japan, and in Turkey. We have 2 codes for building type of structures. We have the code, and the 14th chapter is devoted to the seismic isolated building design. And there is a new code for the seismic isolated buildings also that was published in 2020. The tests. I mean, these isolators are not a shelf product. I mean, you cannot go to the producer and say, oh, I have a 5-story building, please give me this much of isolators and this size of isolators. You cannot say that. I mean, they are tailor-made, specific to your building, and each of the isolators shall be tested. There are 2 types of tests in the course. One of them is qualification test, which is also called factory production test. The other one is the prototype test. The main aim of the tests are to verify the design properties that you used in your design. If they qualify, if these design properties you assumed in your design are correct or not. The factory production test, in some codes, it is required that 100% of the isolators, all of the isolators that you will use in your building should go on the factory production test. This can be done, the factory production test can be done in slow speed. The codes mostly allow this, and it can be done in the, if there is a facility in the manufacturer's factory, inside the by the manufacturer itself. And the loads and the displacements for this test are lower than the prototype test. However, the prototype test should be performed on independent laboratories and in very harsh conditions, the maximum displacements, maximum axial loads, these tests are performed in prototype tests. And the tested prototype units are not used in the structure, but the factory the units that are factory production tested, you can use these products in your building. Of course, if it satisfies your design criteria. There are several testing facilities all around the world, but mostly concentrated in Italy and United States. These are the testing facilities that I collected some information, but there might be some additional ones in the near future. Maybe these ones, this information was 2-3 years old. It might have changed. The largest isolator testing facility, independent testing facility, is at University of California, San Diego, SRMD testing facility. It can test isolators with a vertical load of 53,000 kilonewtons, and it's a 6 degree of freedom testing facility. I mean, you can give a real earthquake record to this testing facility, and they can test your isolators with this record. The velocity is enormous. I mean, it's 1.8 meters per second, and the displacement capacity is nearly 600 millimeters. The second most commonly used testing facility is in Italy, in Pavia, EU Center. The vertical force capacity is 50,000 kilonewtons. Displacement capacity is nearly 500 millimeters, and the velocity is 2.2 meters per second. But the displacement capacity of SRMD, the one in California, is much larger than the AU Center. The displacement capacity is 1.2 meters in SRMD, while at AU Center it is only 500 millimeters. There is another lab again in Italy, Messina. I haven't been there. Eurolab. There is one in Potenza. I have been in Sisma Lab. Another one in Taranto, SysLab, and in Taranto Sisma Lab. There is one independent facility in Turkey, in Eskişehir, which has a vertical load carrying capacity of acting force capacity of 20,000 kilonewtons, and with a velocity of 1 meters per second, and with a displacement capacity of 600 millimeters. Quite good. And the other ones, for example, another independent one is Ankri in Taiwan, and one in Canada, and there are some manufacturer laboratories in China. Hirun's laboratory. It's a very high capacity laboratory, and EPS's facility in San Francisco. And as far as I know right now, again, FIP in Italy has a testing facility, dynamic testing facility in Italy. Let's talk about the isolation applications. This was the number of isolated buildings in the world that was collected in 2015. So it is nearly 7 years old. And you can see that most of the isolated buildings are in Japan, then China, and the buildings that you can see the rest in the other buildings. The Turkey, where we mostly right now work in the Turkish projects. In 2015, it was only 40. Now it is much more than 100 projects. And the difference in the Turkish applications is that the hospitals are very large. Now you will see the world's largest seismic isolated buildings. In Turkey, I mean in Japan, you can see even small residential buildings, maybe 1-story, 2-story high residential buildings with maybe 5-6 isolators only. But in Turkey, the average isolator quantities in the applications is around, let's say, 300 and 400, and there are applications with more than 2,000 isolators in Turkey. We will talk about this. In 2017, a magazine, Engineering News Record magazine, published an article about the world's largest base isolated buildings. It was I will show you the 10 of those base isolated buildings in this magazine by July 2017. The number one was used to be, let's say right now, because there is a new record breaker. Number one is Apple's headquarters in California with nearly 450,000 square meters, covering 450,000 square meters area. And it has 700 base isolators. The second one is in Turkey, Adana City Hospital in the southern part of Turkey, which covers 430,000 square meters. So they are actually very close to each other. The slab that is over the isolation, the slab over the isolation, a unique slab, is from here to here is something like 300 to 300 meters. It's a very large slab, and the building sits on this 300 to 300 meter slab. The third record breaker is the Tokyo Skytree East Tower in Japan, with nearly 230,000 square meters. The fourth one is again from Turkey, Isparta City Hospital, with covering 220,000 square meters. The fifth one, again in Japan, Logistics Park Hino, I don't know, with 210,000 square meters. Sixth one is again in Japan, Logiport Sagamihara, with covering 210,000 square meters. Seventh one, again Japan, Shinagawa Season Terrace in Tokyo. Eighth one in Turkey, in Istanbul, the Sabiha Gökçen Airport terminal, which covers 200,000 square meters. Ninth one in Turkey again, in the eastern part of Turkey, Erzurum Regional Research and Training Hospital. This design was done by Prota Engineering while I was working there in 2011, I guess. So it is the ninth one, with covering more than 180,000 square meters. And 10th one is in Taiwan, a medical center with covering 160,000 square meters. Now, as I said, we have a new record breaker in Istanbul, Başakşehir Pine and Sakura City Hospital. The name Pine and Sakura City Hospital comes from the joint cooperation between Japan and Turkey. It was funded by Japanese banks and constructed in Turkey. So Sakura is the famous tree of Japan, and the pine in Turkey. So the hospital's name is Istanbul Başakşehir Pine and Sakura City Hospital. It covers more than 1 million square meters of area, double of the EPOS headquarters right now. And there are larger hospitals in Turkey being constructed right now. It deploys more than 2,000 seismic isolators. I had the privilege to work as a consultant to the contractor in this hospital as a seismic consultant. So if you want to know more about this design, you can check this publication by the structural designer, official structural designer Arup Los Angeles. They published a paper in ASCE. You can go in this publication and read the details of this enormous hospital. Now I will go a little bit deep on, I will show you some photos from the construction stage for the designs of Prota again. While I was in Prota, I used to work in Prota in 2000, between 2010 and 13. We designed this hospital, one state hospital in the southern eastern part of Turkey. We used friction pendulum isolators by the producer FIP in Italy. The important thing, the friction pendulum isolators are actually very easy to manufacture. If you have a CNC machine, then you can make the concave surface. But the know-how is in this yellow material. Sometimes it's yellow, sometimes it is black. It is the friction material, which is composed of a Teflon-based material. It's called PTFE. So it should resist to high axial loads, and it should have a constant and low friction coefficient, and it should resist to high sliding displacements. So this yellow part is the sliding surface, and this black region is actually the dust cover. You do not want the dust or rubbish or concrete to come on the sliding surface. So you need to have a dust cover. And the companies, the manufacturers' solution is a skirt like that. And you can see the shiny part. This is the stainless steel part that this yellow sliding material moves on it. This is the old testing facility. It was a slow speed testing rig of FIP. Now they have a dynamic machine. And these are some photos from the construction. I mean, the isolators were constructed on top of the basement floor, below the ground floor. So you can see the pedestals, a large size pedestal, something like 1 meter to 1 meter. And the isolators are placed on top of these pedestals. Now you can see an isolator placed on top of the pedestal. You can see the anchors that will go on the superstructure. These anchors work only to friction, to the shear. They do not take any traction forces, tension forces, because it's like a curved surface plate. Then if there is a tension force, there is uplift. They do not take any tension forces. So they are designed for shear force only. And you do not see here, but it will be, I mean, the grout will be applied below the isolator here. You can see the formwork on top of the isolator, where the column reinforcement will come, the base of it. Then the column reinforcement is applied here. Then the rest will be the slab. There were some special solutions for the elevator shafts and the staircase shafts, where, I mean, the main isolator interface is on top of the columns of the basement floors, but the isolators of the elevators and the staircases were on the foundation level. So you have to have a gap around this elevator shaft just to make it move with the principal isolation layer. You can see here the elevator shafts being constructed and the gaps here, and the main isolator interface is on top of the columns. This is another photo from the construction stage. The isolators are placed, and on the right you can see that a part of the superstructure is also being constructed. This is a nearly final photo of the construction. You can see that isolators are on top of the basement floors. Maybe I can, okay, magnify. The isolators are on top of the basement floors, and the basement walls are not continuing to the upper floor, because you need to have your superstructure to move on the isolators. You should not connect anything from the base to the superstructure. It can be structural components, the walls, also pipes or any cables should be flexible at this isolation interface. Another application that I would like to talk to you about is again a design of Prota. Again, I had the privilege to work on this project while I was working in Prota. It's an hospital that was constructed in 1991. It's a retrofit project. First of all, it's not a design. It's a retrofit design project. The hospital was constructed in 1991. It's composed of 16 hospital blocks. You can see the high-rise blocks here, and there are also low-rise blocks. And after 1991, when the construction completed, until 2020, this hospital was not in service. Neither patients entered this hospital. I mean, there was even not only one patient treated in this hospital, because it suffered some fire. Then after fire, it was retrofitted, Then with the code in 2017, the building assessed again, and it was found inadequate for the requirements of the code, and it had to be retrofitted again. Then we have decided to retrofit this building with seismic isolators. This is the plan view of the hospital. You can see that there are several blocks. Each color shows the different story heights and different basement floor numbers. So it was a really complex structure, and it was the first retrofit in Turkey with seismic isolators. It was a really challenging job. The primary isolation surface was decided to be over the first basement floors, below the ground floor slab. You can see the first basement floors, the primary isolation interface and the isolators below the ground floor slab, and the isolators below the elevator shafts and the staircases were on the foundation level. But since at some points there are 2-story levels and at some points there are 3-story levels, you have to make a seismic gap between this level. Why do we do that? Because if you place the isolator on the primary isolation interface for these elements, during a seismic action, if the elevator is in that level, it may lead to casualties, as well as it may interrupt the performance of the isolators as well. So we put the isolators on below the isolator shafts, but these isolators are designed with low lateral stiffness. They were friction isolators with low friction coefficients, just to protect this connection here, because it will act now like a cantilever. So we have to protect this joint. At that time, in some part of the project, we used Probina Orion in 2011. It is the ancestor of ProtaStructure. We modeled the structure with that, and we performed the equivalent linear analysis by the help of Probina Orion. This is the plan view of the isolators, the layout of the isolators. You can see that there are lots of isolators, and this is the construction methodology. What we do first, since the columns, when you cut the columns, they start to move, behave like a cantilever, and the reinforcements are not, they do not have enough strength to resist this cantilever action. So first of all of the columns are jacketed by reinforced concrete jackets. Then it's a technology of Freisash in Turkey, Freisine group. There are 2 clamps, one on top of the column and the other one below the isolator, and you put the hydraulic jacks here. Then you load the jacks. So it's load the jacks with the axial load on the column. So there is a non-loaded part where the isolator will be installed. Then you cut this part and you install the isolators, and then you leave the jackets. So in this case, for example, the load is transferred from the clamps to the hydraulic jacks, then to the below column. And now at the end, the load is transferred from the column to the isolator and then the lower part of the column. Let's see a video of that, and then I will conclude my presentation. You see that right now they are installing the clamps, the upper clamp right now, and they apply a tension, the post tension to the clamps. They stay there with the aid of the friction between the steel plates and the concrete. And there are 9 floors over these hydraulic jacks. Now they installed the hydraulic jacks. They are checking the the magnitude of the force. Now they are cutting the column with a diamond wire. It is being cut. Now they are extracting the cut part. They are installing the lower plate and upper plate of the isolator with the help of the grout. Then they install the isolator to the upper and lower plates, and now the building sits on the isolators. If you would like to know about the seismic isolation applications in Turkey, including the Marmara University Başarılı Research and Training Hospital, and also the world's largest seismic isolated hospital, İkitelli Hospital, you may apply to this journal paper written by me and Professor Mustafa Erdik and my other colleagues. You can check that. Thank you very much. My presentation is over. If you have some questions, I would like to answer them.
Thank you very much, Dr. Shadan, for being here and this wonderful presentation. Seismic design and isolators are interested topics for structural engineers, and ProtaSoftware has been delivering these design techniques for several years. So before we close up, I want to quickly emphasize that we have special prices and payment plan options now available for perpetual and rental ProtaStructure suite licenses. Free annual maintenance, including all updates, maintenance packs, and professional support, along with access to online e-learning and Prota Knowledge Hub are included in our offer as well. You can email globalsales@protasoftware.com or reach us through protasoftware.com to find out more. So if we try to go over our website, we have new web pages available for you. As I mentioned, you can request a quote through filling out this form, and our sales teams around the world will contact you in a day or two to give you information about our special opportunities and payment plan options. And here, this is a brand new trial page which has been released last week. So you can now try ProtaStructure Suite 2021, all products for 14 days for free. All you have to do is to follow these steps. You need to register first. If you haven't done so, you can register now for free through this button. And if you have registered to Prota page earlier, you can click login and request your unlock code and download your trial to try ProtaStructure Suite on your own projects. If you want to continually hear about our updates and events, feel free to follow us on social media and subscribe to Prota newsletter. This webinar recording will also be available at Prota Help Center and Prota YouTube page in a couple of days. Thank you for your time and see you at our next Prota event.